Hello Mehmet. Someone called our office the other day, who had a project in Iraq. They said that this project is a huge project, 21,000 square meters. First they asked for a demo, and then they thought that your program cannot solve our project. This 21,000 square meter project has been solved before. They solved it with local software, and the result was 80 kilograms square meters. But I know you have solved this project already, and I also know that you got much lower result and a solution, which is 35 or 40 kilograms square meters. I was wondering if you could solve this project with our program and show us.
The project is in Iraq. Our project consists of 3 halls. Our first hall is 50 meters, our second hall is 30 meters and the other is 30 meters too. Column lengths are 9.5 meters. They said the gaps between axles are not important. The total length of the building is 200 meters. There will be one expansion gap at the 100th meter. Therefore, while solving the project, we will first solve the 100 meters.
So, which standard will we use when solving this project?
They said we can use Turkish standards. But this place is actually in Iraq. So we have to use American standards. I will use Saudi Arabian standards in this project because it is the closest place to Iraq. They are neighbors and I will use it to get their earthquake parameters. If you want, let's start the project like this. We are opening a new project. This will be a PEB type structure, it was intended to be so. Let's keep our truss length of 50 meters, column lengths of 9.5 meters, and 6 meters between axles. Let's remove the column first. Let's fix the features of our truss, 50 meters. I chose this place as 2.5 meters, we were free about it. I want the distance between the purlins to be around 1.5 meters, so I divided it into 18. With 1.40 intervals. DC-wise the initial height of the beam, 1 meter. We make the width of the DCX column in the corner 1.2 meters. DRY is height at ridge, 1 meter. In the DCX corner, the part where the tapered section will continue along the purlin is exactly 6. I have selected 7 from the DRY corner, and how many purlins from the NDRX ridge will be variable. This is how we arranged our first roof system. I added another one of the same. Let's edit it now. This time, the span length is 30 meters and the ridge height is 2 meters. I want the distance between purlins to be 1.5 meters again, 11 of them. DCY is the height of the corner tapered beam section. I will not change it. Let DCX stay at 1 meter. I also change the height at the ridge to 0.8 meters. There is 3 reinforced sections in the corner. The reinforced section on the ridge, that's 3 also. Our second truss is here now. Our third truss is the same. We see a structure like this.
We will probably enlarge our building now.
Now let's enlarge our building. It was supposed to be around 100 meters. I'll make it 102 meters, since it's a multiple of 6. It will be such a huge building. Now let's see our loads. We use EN 1991 in Turkey, but since this project is in Iraq, we will use the Saudi Arabian standards, since they are neighbors. Occupancy class is 2. Our roof cladding is sandwich panel. There is no solar panel on it. This is Iraq, so we will take the snow load as low as possible. I'm thinking of a snow load of around 0.2 kilonewtons per square meters like this. In terms of wind load, this place will be in category C as it is more than 9.1 meters. It's a closed building. Internal pressure is 0.18. This is the wind map of Iraq. A wind of around 33 meters per second is mentioned. So we're somewhere in that area. At 74 miles per hour, 33 meters per second is achieved. Now let's come to thermal loads. Let the internal temperature of the building be around 25 degrees in summer and around 25 degrees in winter. Since this building is in Iraq, the air temperature can be 50 degrees in summer. The lowest temperature in winter is 15. Let the building construction be done at 25 degrees. Considering these parameters, our building will extend according to 27 degrees. It will also shorten according to -5 degrees. Let's come to the information about the earthquake load. This is the Saudi Arabian Building Code. Our building is on the Iraq border. Let's use RAFHA values. SS value is 0.6. S1 value is 0.2. My soil class is Group D. The building importance factor is 2. According to this information, we can now see the active loads in the building. In the meantime, there will be snow accumulation between those two roofs. Even if our snow loads are low, snow accumulation is taken into account. These are our wind loads. We can see the wind loads coming into each of the roofs. The distribution changes when the wind is from the front. We can transfer these to the secondary building elements. We will calculate the roof and wall purlins according to these loads. Then we transfer these loads to the main carrier systems. We will design our columns and beams according to these loads. Now let's come to roof purlins. In roof purlins, all our purlins are the same. I saw that the C200-15 profiles would be sufficient for purlins. Our second truss is C215. Even if it's at 92% capacity, it's enough. The main load here came from the wind. There was snow on vertical loads. Here the wind is stronger. Thus, we have made our roof purlin calculations for all our trusses. Then let's come to the girts. Let our wall girts also remain as C215. Let's look at the girts on the right side of the building. I changed them to C215 as well. While we're here, let's add lateral supports to the columns in the girts on the right so that we don't do it again and again. Let's do the same with to the right side columns. They are okay too. Then we can move on to changing our column sections. Main columns. The leftmost column. The facade cladding is sandwich panel. This column is also 200-20. I choose a 600-15, 200-20 column with a height of 600 mm. Let's assign the cross sections of the columns together. There is no cladding on them. Again from the 200-20 series to the 500-12. Now the far right column. I don't want any type variety in the far right column, so I will use the same profile again.
There's facade cladding on this one.
Right. 220. 500-12. Steel grade is also S235. In this way we have defined column sections. Now let's come to the rafter cross sections. We will choose our beams from the 175-15 series. The first is 600-12. Then the second truss, in the middle, 458 from the 150-10 series. And the other will be the same. 458. Now let's assign lateral supports to our rafters. 25 meters in the middle. We define lateral supports to the 50-meter beam, by skipping from right to left. Then the middle roof system. From the right to the left of 65 meters. Similarly to the rightmost. Now let's do static analysis. The strength of the rods we used in the braces are not sufficient. On the YZ axis. There are also problems with the middle rod bracings. We'll check these again shortly after we put the wind columns in.
If the problem persists, are we going to use tubes?
If not, we will use of circular hollow section profiles. It is green when viewed as such. What's not green? There is a lateral buckling problem on the 25, 26, 27 over there. We forgot to put one lateral support in between and the program realized it.
The program warned us.
We know that sections are not a problem. Let's not look at it again now, as I'll be repeating the analysis in a moment anyway. How much does our solution cost? Let's look at a cross-section first. Let's check if there is something bothering the eye. It looks pretty good. It doesn't seem like much of a problem as the sections are sufficient. Side columns are connected from the top, and there are side beam connections between them. Considering these connections, I chose the flange thickness of the column sections a little thick. Now let's look at the cost. So 30 kilos right now. Now, at this stage, let's check their connection design. Now let's solve the corner beam column connection. Connection design calculations will be made according to the following load combinations. It's %574. Why? Because the plate thickness is insufficient. I changed these to 25. Now we examine the connection. I think end plate is a little wide. It's better now? Let's look at the results. 105. If we also increase the thickness of the bolts, we will see that it is below %90. This connection is okay. Now let's come to the calculation of here. There is some problem with plate thickness and welds. The plate thickness is selected as 15. I change it to 20 mm. Let there be 3 bolts in the middle. 56% weld thicknesses. The rafter will be welded to this plate by 6 mm leg welds. Then the middle one is the same. Let's not make different additions in connection attributes. More than enough. Let's increase the number of bolts here. 5 bolt rows. It's better now? Let's increase the plate thickness and the bolt diameters. Welds remained very limited. Let's increase the thickness of the welds a little. Better now. This is similar to previous beam splice connection. Let's change the weld thicknesses. Let's use M20 bolts and it's now okay. I saved this too. I checked Connectiondesign results. It's more than enough. Now we come to the side-connected column beam connection. End plate thickness is 20, width is 225 mm. Let's reduce the number of bolts. The distance between the bolts should not exceed 20 centimeters. In order not to take much of your time, similar Connectiondesign calculations have been prepared by speeding up. Now we come to the account of the column base plate Connectiondesign. The pad foundation will also be calculated. Our column base plate is quite small compared to our column 500 to 900. For this project, 30 mm. Such a column base plate as you can see. Let's look at the results. The thickness of the column base plate is insufficient. 40 mm thickness is enough. Let's increase the number of bolts in the flange by 1. The distances between the bolts on the body are too far, let's fix them. Let's enlarge the plate and bring the bolts in the flange closer together. The flange requires 2 rows of bolts, not 1. Now the results are enough. There is a problem with the pad foundation dimensions. Let's see if we can shrink the pad foundation dimensions a little more. The foundation used here is 4 meters by 3 meters. Let's make it 4 by 2. Now let's fix the reinforcements of the foundations. Let's set rebar diameter as 24 millimeters. They are 14 centimeters apart. Again, I make sure that it is under 20 centimeters. We can reduce the numbers a little. Let's reduce the diameter. There is a connection like this with 97% capacity. It is a bit unusual, but since the building is also unusual, this is only possible with such a column base plate. If we had made the base plate connection of the column with the foundation as a simple support here, maybe our column base plate would not have been this big and our pad foundations would have been smaller. But this time our column and rafter sections could have grown. I haven't tried it yet. Now let's look at the pad foundations of the middle columns. The foundations of the middle columns may be relatively small. When we look at the results, we see that there is a problem in the plate thicknesses. Let's use 500 to 700, 30 millimeters, M24 anchor rods. Column base plate thickness is 40 millimeters. It's enough now. We can reduce the dimensions of the foundation by looking at the soil bearing capacity. Let's change our foundation dimensions and try 240 to 150. I think this way is enough. Let's check out our foundation reinforcements. 20 mm diameter reinforcements. Just like this is enough. We had a small foundation for this cairn. Let's use same the values of the previous foundation. Let's look at the results. Sufficient. I don't want any variety. Soil bearing capacity is insufficient, so we are increasing our pad foundation dimensions. Longitudinal reinforcements are insufficient or at limits. Let's increase one by one. Much better this way. The plate thickness can be reduced, but I won't change it for variety. In this way, we have completed the connection calculations. Let's complete our missing calculations. One of them is that we didn't put the lateral support over there. Let's put it first. Now we will add end posts to complete our project. We chose wind columns and chose sandwich panel for shield cladding. Numbered 6, 12, 18, 24, and 30. The back of the building. Sandwich panel cladding again. 6, 12, 18, 24 and 30 meters. Then the ones on the side. 4 and 4th from the end. 4, 9, 13, 18. Same on the other side. The rear is 4, 9, 13 and 18. In this way, we have indicated the locations of our wind columns. And now we must assign the end post cross sections. Let's assign them. The same sections will be used in all wind columns. All my end posts cross sections are H600:12 to 175 to 15. Now we repeat the static analysis. After the wind columns come, we will make the calculation of the roof braces and the wall bracings. Because the sections of these elements need to change according to the wind coming from the front shield, our side bracings were not enough as we expected. We can use CHS profiles or large rods on this axis. But I will prefer to use a CHS profile on this axis. Likewise, on the right axis, instead of the 20 rod. Now let's check the sections of the front shield end posts. We have chosen our end post cross sections a little larger. Thinner profiles could have been used. It was also possible for us to reduce the section of that raft on the front shield. Let's fix the sections of the rods and braces on the YZ axis. We will use 30s rods, not 24s. We're also going to make the stability beams a little larger. I'm changing the braces here to D30. I also changed the stability beam to SHS126. Those on the middle axis will be slightly larger. This time I want to use CHS profiles. 89 to 6 mm. We also enlarge the stability beams and make them SHS150 to 6 mm. In the YZ axis, we make SHS150 to 6 mm, as in the YZ axis. We also change stability brace to CHS 89 to 6 mm. I will also change YZD axis bracing elements like as YZ axis. We repeat the static analysis. In YZ axis, wall bracing elements capacity ratios are in acceptable limits. In YZB axis, 89 to 6 CHS profiles are insufficient. We can also change the first and last ones. YZC axis, first and last row bracings have same problem. Let's show you how to swap first and last row bracing cross sections. In YZB and C axis we try to use CHS 114/6 instead of CHS 89/6. In YZA and E axis, I want to try D32 instead of D30. After this stage, we will do the static analysis and we will finish our project by looking at the total cost of the building. The results are slightly better. Let's look at the intermediate axles. It was almost okay. We could have chosen a little larger than this. So we had to choose a thicker one. There is no problem with YZD. Let's see the 3D model of our structure as it is. And here is our model. Let's take a look at what we're doing now. You can see our lateral supports in the rafters. These are necessary to prevent lateral torsional buckling. Our connection details have arrived. We have lateral supports in the columns. We also have lateral supports on the side columns. Our wall purlins on the front shield facade is there. It actually looks like a pretty big building. The connections of our rods and the supported structures of the purlins can be seen. Whilst we're at this stage, let's get the actual cost of our build. The actual cost of this building is 36.33 kilograms/square meters with the wind columns and the purlins on the gable facade. As Tolga said at the beginning of this video, this building was solved with a local software in Tokyo and weighed 80 kilos per square meter. And this is our solution, which is only 40 kilograms per square meter with casualties. This was the figure that we suggested to the project owner company, and that we said we had solved it. With this calculations we have finished our project today. See you in the next video. Goodbye for now.